So welcome to the Ashby Village Science and Ideas Group. My name is Joe Evinger, and I, with Hillary Naylor, help coordinate the group's events. All of our members have lots of educational and work experience and detailed backgrounds, but we all share a common interest in science and new ideas. We have over 50 members and another 50 on our guest list. We have a different guest speaker each month who speaks to us on a topic related to science and ideas, and we rely on our group members, the Ashby Village Arts and Culture Committee, Ashby Village members, presenters, and anybody else who wants to give us a lead for a new speaker. Besides our presentation today, I'm actively recruiting speakers who might speak to us in the oncoming months. Here are some of the upcoming topics. In August, I have an application into NASA to have a speaker, but I haven't heard back yet, so stay tuned for that. In September, a geologist is going to talk to us about volcanoes, in particular super eruptions and how one might occur at Yellowstone. In October, one of our own group members, an anthropologist, is going to give us part 3 of his story of human migrations out of Africa. Later this year, one of our members has a son who's working, and we're trying to arrange with him to speak to us about mass extinctions and ancient climate catastrophes. We invite everybody to come to our presentations. You don't have to be an Ashby Village member. Just send me an email and let me know you're coming. On to the topic today. The environment is a big concern to all of us. Today, we are here to learn about a relatively new environmental concern that is relatively new to me. He will tell us about a number of different topics on this, and I'll leave that to Dr. Kim Juniper to tell us that. Kim Juniper is a professor of biology at the University of Victoria, Canada. His primary focus is his research on the biochemistry and ecology of submarine and hydrothermic systems. Dr. Juniper's research on deep sea vents encompasses the fields of microbial biology, biomineralization, and benthic ecology. I had to look up that word benthic, but I take it has to do with the seafloor and anything underneath water, the soil below that. Other areas of his research include microbial biology of deep sea sediments and the seasonal dynamics of Arctic sea ice microbial communities. The presentation of his topic today is the battle for the abyss, mining, conservation, and bioprospecting interests square off on the deep sea. And with that lengthy introduction, I now pass it to you. Thank you very much, Professor Kim Juniper, for making a presentation to us today.
Thank you very much, Joe, and good afternoon, everyone. I'm speaking to you from Science World in Vancouver, Canada. Science World is located on the unceded traditional territory of the Musqueam, Tsleil-Waututh, and Squamish nations. I've actually been here all day at Science World for the opening of an ocean stewardship exhibition presented by a number of Indigenous groups up and down the coast here. They all arrived by canoe early this morning and been sitting through all sorts of really interesting talks about the responsibility of all of us to do our bit to conserve ocean biodiversity. And I was mentioning to Joe earlier that 2 weeks ago, I was at the UN Ocean Conference in Lisbon, Portugal. And this conference was attended by 12,000 people. And interestingly, there was a group of millennials who were pushing very hard during the conference for a 3-year moratorium on deep sea mining, which is due to be legal about a year from now. And so for the first time at one of these normally sort of formal staid UN events, we had people pulling up signs in the back of the room and going around having their badges scanned by the UN security people. So that, it gave a little bit of energy to the whole conference, and I went away with a very positive feeling about it. So what I'm going to do today now is to explain to you what they were all upset about. and where this fits in our relationship to the ocean. And as I said, this is really a battle for the abyss. It's not just mining interests that are at play here. There are the interests of those involved in biodiversity conservation, bioprospecting for biotechnological exploitation of marine species. We all want our piece of the pie, and this is all kind of coming to a head right now. As I mentioned, this to the point where people were protesting at a normally really boring UN meeting last week. So where are we at now in terms of our general society's appreciation for the deep sea? I think this can probably sum it up right here. This slide is a cartoon from the New Yorker from the early 1980s. These ladies are having afternoon tea and stating, if you've never seen it, why would you care about it? If you don't know anything, well, you got better things to worry about. So that's kind of where a lot of us are at right now. And hopefully by the end of the next hour, I can get all of us beyond this particular point. So hang on here, whoops, we got yeah, let's go, there we go. So the deep sea, believe it or not, is the largest habitat on the surface of our planet. Dry land occupies 29% of the Earth's surface. Water less than 2 kilometers deep occupies another 11%. So that leaves 60% of the surface of our planet is covered by more than 2 kilometers of water. And that really amounts to something on the order of 240 million square kilometers of seabed, or 1 billion cubic kilometers of deep ocean water. Remember these two numbers here, because I'm going to be coming back to them a little later when I talk about how we are exploiting the deep sea. But as you can see, it's huge, and most of us don't know much about it. To begin with, ecologically, the deep sea is an energy desert. There's no light down there. Light in the ocean usually cuts out at about 200 meters depth, and we're down below 2,000 meters. So that means there's no food being produced by photosynthesis. So if you live down here like this sea cucumber here on the seafloor, you're entirely reliant on organic debris or fallen carcasses that are coming down from the surface ocean. You're really kind of at the bottom of a garbage can. And it's also really cold. Water temperatures are somewhere around 2 to 4 degrees Celsius in the deep sea, just barely above freezing. So that means that there's low abundance of animal life, really slow growth because it's an energy desert, but amazingly, really high biodiversity. It's still poorly sampled. We haven't really, because of the access issues, but there are estimates out there. There's anywhere in between 500,000 and 10 million species in the deep sea alone, compared to the current estimate of the total number of marine species is somewhere around 250,000. So that just tells us there's a lot more to discover down there if we keep sampling. So right now, our society is primarily making use of space in the deep sea in terms of exploiting deep sea resources. Although that huge, 240 million square kilometers, that's a pretty good dumping ground. No one lives there. We can get away with throwing a lot of stuff down there. For quite some time during the 20th century, medium and low-level radioactive waste was packed into barrels and then dumped into the deep sea at designated radioactive dump sites. We don't do that anymore. That was essentially banned in the 1970s and 1980s. Another thing we do in the deep sea is we got large structures like oil drilling or production platforms that are too expensive to scrap. Well, we can just take them out there and sink them to the bottom. And munitions, expired munitions, particularly at the end of the Second World War, there were a lot of both explosive and chemical munitions that had accumulated during the war, and we didn't want to stockpile them. So most countries with a coast essentially had designated munitions dump sites. And if you look at marine charts, for example, you see quite often warning signs on the charts, don't go here, don't fish here, don't drop your anchor here, because there are still munitions. In the future, I'll come to that in a sec. We are also using the deep sea as a deposit site for dredge spoils or sewage sludge. So when we are dredging shipping lanes and ports to keep the water deep enough as they're silting up, What do we do with the dredge swells? Well, we take them out to sea and dump them in designated dump sites. And then looking ahead to the future, even though a lot of these practices are fading for various reasons, we are also looking at this huge volume of ocean water and space in the deep sea as a site for CO2 sequestration. So this could involve simply injecting liquefied CO2 that we've captured from the atmosphere into the seabed, and it'll stay down there in a little puddle at the bottom of the sea, either as dry ice or as a pipe, et cetera. So that's one way of addressing some of the climate change challenges by pulling CO2 out of the atmosphere, dumping it in the ocean. And then there's also a lot of research being done right now to look at direct air capture of CO2 at sea, and then injection below the seabed into volcanic rock on the seafloor, where CO2 actually then form rock by reacting chemically with volcanic rock with basalt and stay there essentially for forever. So that's really being looked at quite seriously. And another benefit that we've all been driving, perhaps unknowingly, from the space of the deep sea is that the ocean has really been serving as a huge climate change buffer. The ocean volume, it's estimated, has absorbed about 90% of the human climate warming. So rather than that heat going into the atmosphere, it's gone into warming up the ocean. Since you can see about 1980s, it's just slowly warming up. This is not temperature. The scale here is in 10 to 22 joules. But it just lets us know that every decade we are adding more heat to the deep sea that would otherwise be impacting and causing even more severe climate actions. And also about 25% of the fossil fuel CO2 that we've been pumping into the atmosphere since the beginning of the industrial age is actually dissolved in seawater rather than accumulating in the atmosphere and adding to greenhouse effect. So, thank you, 1 billion cubic kilometers of seawater. You've been protecting us unknowingly from paying the price for fossil fuel burning. The only living resource that we've been exploiting in the deep sea in the last while have been fisheries, primarily on seamounts. These are underwater volcanoes in the deep sea that rise up from the seabed, and you get a lot of fish accumulating around them. And if you look at this graph here, it shows you in the Pacific, Indian, and Atlantic Oceans, the history of catches from these seamount fisheries. As you can see in the Pacific that it peaked somewhere around 1990, and then the fisheries started to collapse. So we moved on to the Indian Ocean and the Atlantic, doing the same thing. There are more seamounts in the Pacific. That's why we started there, and that's why we're still catching more fish there. But this is a typical haul from one of the seamounts. This is the orange roughy, which was a very popular fish. But this fish lives about 80 or 100 years, and they don't reach sexual maturity until they're about 30 years old, which means that the young ones can't reproduce until they're about 30. So we're hitting them pretty hard right now. But what I'm talking about today is ocean mining is now on the horizon, the next phase of human exploitation of the resources of the deep sea. And we're doing this because we are consuming metals as our global economy is growing. This chart here just shows you global copper consumption trends since about 1980. Just pay attention here, for example, to the trends in China, where as the Chinese economy has grown, as we build more factories, build more big mega cities, we need more copper for wiring. But that's not the only reason for looking to the deep sea for mineral resources. We're also very much interested in manganese, which is used in hardening steel, cobalt, which is an important ingredient in rechargeable batteries, copper wire, as I mentioned, and then nickel, which is another important component for hardening steel that's used in wind turbines for producing green energy. So there are three major deep sea sources of these types of metals. We have what are called cobalt-rich ferromanganese crusts, which are found on seamounts, and I'll tell you about that in a minute. There we find manganese, copper, and a lot of rare earth elements that are all combined in these crusts that are, well, they can be several centimeters thick or even thicker. And then the manganese nodules, found in a different part of the ocean, I'll show you where. They contain manganese, copper, nickel, titanium, and rare earth elements. And then the polymetallic sulphides that were found that are formed at deep sea hydrothermal vents, these hot springs on the seafloor and volcanic areas of the seafloor, they have accumulations of copper, zinc, gold, and silver. So if you're just mining them for copper and maybe zinc, the icing on the cake is you're going to get a little bit of gold and silver at the same time to help pay your expenses. So where are they, these minerals? Well, the cobalt crusts that I was telling you about are found on seamounts. These are underwater volcanoes. That's where I was showing you the fishery a little bit earlier. So these are found at depths between about 800 and 2,500 meters depth. And they take millions of years to form these crusts on the sides of the seamounts. So seamounts are essentially big pieces of volcanic rock that are sticking up out of the seafloor, a little eruption. And then the seafloor massive sulphides that contain copper, zinc, gold, and silver, they are found on these volcanic ridges, what we call mid-ocean ridges, anywhere between 1,000 and 4,000 meters depth. And they are produced by hot water jetting out of the seafloor, and it's very rich in metals, and they precipitate around the openings of these springs. And then the polymetallic manganese nodules are found out on what we call the abyssal plain, the flat part of the seabed, and they're quite deep. They're anywhere from 4,000 to 6,500 meters depth, and they're scattered around the seafloor. So let's look at these individually. First of all, where are these found? Primarily the crusts. The seamounts that we're interested in that have these crusts are found in this area of the Pacific. The major manganese nodule provinces that are known right now, there's this very large one here in the Central Pacific that we'll come back to, another one in the Indian Ocean, and another one here off the coast of Chile. And then the polymetallic sulphides are found on these volcanic ridges that are sort of like seams of a baseball that go all around the surface of our planet. And every one of these little red dots is a known location of hydrothermal vents and deep sea hot springs. So what are these mining operations? How will they work? So they will be done remotely with what are called seabed mining machines. So these machines will be operated, connected by cable to a surface vessel, and they will collect and essentially pump the ore up to the surface. And there'll be a surface support vessel that powers and operates the mining machines themselves, and then does what we call dewatering of the ore material. So separating the solid bit from the water that's essentially used to turn into a slurry and pump it back up to the ship. And then there'll be a shuttle vessel that'll be coming out to meet the support vessel that could be parked at a site for months, if not years. And they will be offloading ore and taking it back to shore for refining. So these seabed mining machines are going to be operated like a lot of remotely operated vehicles that are used right now for deep sea science or for maintaining drill platforms, for example. So you'll have an operator on a stick with a joystick, on the ship with a joystick, essentially looking at screens that allow him to see what the vehicle down there is seeing. And the operator will be driving the vehicle back and forth on the seafloor, doing its thing. And here's an example of some production tools, as they're called. And I call them the new monsters of the deep. This is a set that was produced by Nautilus Minerals. It was a Canadian company based in Australia that had a project to do some seabed mining of polymetallic sulphides near Papua New Guinea. So they built their machines and tested them, but then they ended up in bankruptcy. So their machines are still sitting around. So they will work in tandem, these machines. So there's the terrain leveler, which essentially knocks everything down. And then an ore harvester that'll kind of move things into windrows. And then finally the ore crusher will come along and scoop things up, crush the ore, and then pump it back up to the surface vessel as kind of a slurry. So let's look at how these individual mining operations work, because it depends on what you're going to be mining. So for the crusts, which are found on seamounts, we're essentially going to be down there scraping and dredging the slopes of the seamounts. And it's being proposed to be done in sort of 20 square kilometer blocks, which would be the size of a day's work, so to speak, for these mining operations. Otherwise, they're just not economically viable if you don't do it at this scale. So this is a bathymetric chart of the bathymetry of a number of seamounts, and you've got the size of these individual mining blocks here are laid out. These are all 20 square kilometer blocks. The manganese nodule operation will be very different because these nodules, as you can see right here, they're just sitting there on the seabed waiting to be scooped up, as one geologist would say. And the scale of operation, or here we're talking about 20 square kilometers. Well, we're talking about thousands of square kilometers per operation in order for these to be economically viable. So there'll be machines essentially going along, scooping these things up on the seafloor, and then pumping them back up to the support vessel. The polymetallic sulphides, on the other hand, are pretty small areas. So they're found in an area that's the size of a couple of football fields, but they can be maybe 100 meters thick on these deposits that they build up. So that will be very concentrated, and that's why you need machines like this that are essentially going to excavate their way through this. It'll be a bit like open pit mining for coal, and they're essentially going to go and remove it all and leave a hole in the bottom of the ocean. So most of the excavation areas are going to be less than a square kilometer. So what do we decide? Okay, what's this going to do to the environment? What's this going to do to the ecosystems and biodiversity on the seafloor? So I've split this into, looking at what's going to happen in the surface ocean. Well, there's going to be a lot of noise generation from these, fleets of these vessels that are parked out here. In addition to the power generating requirements for the normal operation of a ship, they're going to have huge generators on board in order to drive these machines on the seafloor, operate these massive pumps that will be bringing the ore back up to the ship. So this is going to be a source of noise and obviously a source of CO2 generation as well. And then the water column, the ocean water column, is going to be impacted by both dewatering plumes and collector plumes. So what I mean by dewatering plumes is, when we slurry the ore and pump it back up to the surface here, it goes through a screen. We keep the hard stuff, the particles, and then we have to get rid of the wastewater, so to speak. So it's going to be released at depth. They are clever enough not to release it in the surface ocean where it's going to affect plankton growth, but it's going to be released at some depth where no one's going to complain, but it will be impacting the water column ecosystem. And then the collector plumes, right at the seabed where these machines are driving along, stirring things up, they will be generating a big cloud of dust, like a tractor plowing a field on a dry day. And this is an area of the seafloor where we measure sediment accumulation from the surface ocean at the scales of millimeters per 1,000 years. So that's the only reason why these manganese nodules are still sitting on the surface. So this is an environment that does not normally get a lot of sediment fallout from the water column above. So we're going to be radically changing things. So on the seabed, in addition to the direct mechanical disturbance from these mining machines, there's going to be a lot of sedimentation from both the dewatering and then the near bottom or collector plume. And each one of these deposits are habitats for specialized deep sea species. The crusts on the seamounts. The seamounts themselves are colonized by a fauna of deep water corals and sponges and as I showed you earlier, a lot of long-lived fish species. The manganese nodules, they're invertebrates that live both right on the nodule surface, like this tiny little sponge we see here, as well as beneath the nodules in the sediments. And then the polymetallic sulphides that are found at deep sea hot springs, this is scientifically really fascinating because these are what we call extremophile animals and microbes that can tolerate high temperatures, heavy metals. There's a lot of interest, scientific interest in this, and a lot of interest from the biotechnology industries as well. So what I'm going to do now for next few minutes, but first of all, I'm going to ask if there are any questions. I've sort of gone through introducing these different habitats. And then what I'm going to do is to go through this evaluation framework, the way of looking at how individual mining operations are going to affect these different environments by asking questions like this. So are there any questions about my general presentation of these three different habitats and the mechanics of the mining operations?
Diane had a question.
Sure.
Diane, do you want to ask a question? I could just read it. She asked that you comment on the idea that life first evolved in the deep ocean. You want to add to that, Diane?
Well, that's my question. You just read it perfectly.
Okay.
There certainly is a very viable hypothesis out there. The life first evolved at deep sea hydrothermal vents, where there's a lot of heat energy. There's these things can be like bioreactors, and because it's in the deep sea, the early life that evolved there would have been essentially sheltered from some of the more disastrous comet impacts and asteroid impacts that affected the first few 100 million years of Earth's history. So it's certainly a viable hypothesis. I'm not about to say that that is the only place it could have happened, but it is there's certainly a lot of interest in deep sea hydrothermal vents as a place. And when I come to actually talking about the vent fauna, I'll come back to that as well. Any other questions?
Joe has a question.
Yeah.
You've spoken about these manganese nodules. Where do they come from?
Okay, yes, the manganese nodules are formed by spontaneous precipitation of metals from seawater around some kind of nucleus, a bit like, you know, raindrops form around dust particles in the atmosphere. So what happens is that there's a lot of manganese nodules have shark's teeth at the core. So you just, because this is an environment that is very sheltered from current, there are no ocean currents or barely any ocean currents down there, very little sedimentation. You get metals just precipitating out of seawater spontaneously on hard surfaces. And then they'll start to accumulate in layers. And these things take millions of years to form. And they stay on the seabed because there's no sediment falling down. So this is just essentially spontaneous, what we call hydrogeneration of metals. And they will selectively, if you cut some of them in sections, you can actually see layers where they've had, you know, periods of more rapid growth than others. Any other questions?
I have a follow-up question. I'm going to try and keep my questions and share for others, but who polices all this mining once you get off the borders of all the countries?
Yep, I will tell you about the police
that
a little later.
Okay.
I'm coming to the police part, yeah.
Okay.
Essentially, and the story is essentially we put the fox in charge of the henhouse.
I was afraid of that.
Okay, so I'm going to look at these three individual mining operations in just a very simple framework. So in terms of valuation, you know, what's there biologically, and what is the value of those organisms that are living there to the larger marine ecosystem, and of what value are these organisms to society in terms of ecosystem goods and services, and then the recovery trajectory, you know, after we finish mining, how long will it take this environment to recover? Or as we say in British Columbia forestry, how long will it take it to green up? And then what does that mean in terms of spatial planning considerations for setting aside reserve areas and things like that? So let's go through these three different types of mining operations one at a time. So starting with the crusts. So there's been a fair bit of research done on fauna on the Hawaiian seamount chain here in the Pacific, from submersible and ROV dives, and there are a number of technical reports that NOAA has put out that describes the fauna that live right on these crusts. So you can see this is a beautiful big deep water coral living on these crusts. So far we have identified about 967, we're calling them species, but they all haven't been sampled and classified by people who describe species, but let's say 967 different organisms that are specialized living on seamounts. And in addition to just being species and being there, in terms of ecosystem function, one thing they do is called biofiltration, because of the sponges and the corals, as you can see at the summit of this little seamount, they're constantly filtering particles of plankton out of the water here. And by doing so, they are essentially impacting the ecosystem of the surrounding water column, and they're pulling out organic matter, processing it, and turning it into biomass right on the seamount. So that is the one ecosystem function that we're able to assign to the organisms that live on seamounts. So what I did is I got together with a colleague from the University of Hawaii, and we said, okay, so how much biofiltration capacity would we lose from, taking out 20 square, one mining block, one sub block on one of these seamounts? So how do you make that kind of calculation? Well, what we did is we went about looking at some experiments that she'd done in her lab, where she took what she called nubbins, little pieces of coral from the top of the seamounts, attached them to a plate in an aquarium, stirred the aquarium with a little stirring motor, and then put in some particles for them to filter out the water. So you can actually measure what's called a clearance rate, how many grams or how many kilograms of particulate material can each of these little coral polyps pull out of the water in a day. And then you extrapolate up to the big scale outdoors. And we essentially estimated that every day there are tons, literally tons of particulate organic matter that are being pulled out of the water column by the organisms living on these seamounts, turned into biomass. What's that doing? That's obviously controlling the transparency of the water column and affecting fouling for other organisms. So that's not a small number, tons per day, especially in the deep sea where there's not a lot of suspended particulate material in the water column. Okay, so let's come back to our little framework. Well, so far, in terms of the crusts, we know that there's about 1,000 species in the Hawaiian seamount chain, and we need to look elsewhere. Are they rare or unique? Are they only found on crust? Possibly, but we, people hate it when scientists say this, but we need more data. Okay, but we don't know enough to say that they're not entirely specialized. And in terms of ecosystem function, well, the corals, they create big physical habitat for smaller organisms, even for fish. And then both the corals and sponges filter seawater, as I showed you. So what is their scientific and cultural value to society? They really are biodiversity hotspots in the deep sea. So for society as a whole, that's important. And for science, we love going to seamounts because of the biodiversity. It's a great place to study the biology of different organisms, et cetera. And the potential economic value, well, the only one that we know about so far is the one we've half destroyed, which is the seamount fisheries, but they will recover. So recovery, these crusts take millions of years to form, and these organisms that grow in the crust, they grow really slowly. So, it can take this sponge or this coral here 100 years to get to the size that we're seeing right now. So that gives us a feel for how long it's going to take this area to recover from a mining operation that is essentially going to scrape them all off the slope and crush them and pump them to the surface. So spatial planning wise, this map here of the Hawaiian seamount chain shows you inside this area here is the area we know there are crusts on seamounts. We don't know much about here. So, do we need to protect crust habitat, or if we just leave a few seamounts alone that don't have crusts, will that be good enough to sort of preserve a population that could eventually recolonize this? We don't know yet. It's one of the least studied of these. Okay, polymetallic sulphides, on the other hand, are very different environment. They're formed in deep sea hydrothermal vents. There's the deep sea hot springs on these volcanic ridges. And the organisms, unlike these tube worms here, they directly colonize, areas of active seawater discharge and mineral deposition. And there are hundreds of species that are found only in this environment, which means, and there's a really high degree of genetic novelty, which means in addition to being just a unique species, a lot of them are really weird. This tube worm here, for example, it has no mouth, no digestive system. It lives entirely by taking hydrogen sulfide out of the seawater, dissolving it in its blood and pumping it down to its symbiotic bacteria that live inside it. So this is the tube worm again here. So these hydrothermal vents are really what we call an energy oasis for a lot of specialized ecosystems, because there's a lot of hydrogen sulfide in these hydrothermal fluids. It provides energy for what's called the chemosynthesis of new organic matter. So there's no light there, but we can produce new organic matter by combining dissolved oxygen and seawater and using it to oxidize hydrogen sulfide, turn it into sulfate. And that releases energy that then can be used to fix carbon dioxide into organic matter, turn it into sugars, like plants do with solar energy. Well, these guys are doing it with chemical energy. It's called chemosynthesis. So unlike the rest of the deep sea, where as I mentioned in the introduction, where organisms are very few and far between and grow very slowly, this environment has a high biomass, rapid growth, and really low diversity, because you have to be pretty tough to live here. Low animal diversity, but a really high diversity of microbes. Hang on here, I just got to have a swallow of water. And because of the extremophile nature of this environment, there's a lot of interest in potential genetic resources at hydrothermal vents. There's a small number of animal species, huge unquantified diversity of microbes, but these are organisms that can grow at high temperatures. They have resistance to heavy metals, and they have unusual symbioses. So why would this be of interest to biotech? Growth at high temperatures means we produce enzymes that are thermostable, and we all know that chemical reactions happen faster at high temperatures. So if we have thermostable enzymes, we can produce some high value chemical products by essentially heating up the mixture and putting in the enzymes from these organisms. Resistance to heavy metals, well, we all know we're all worried about heavy metal pollution, and the more we can learn about how organisms can deal with heavy metals, the better off we might be in terms of treating it and cleaning up sites. And then the unusual symbiosis is rather interesting. The two worms that I was showing you earlier, they have bacteria that grow inside a specialized organ. These are the bacteria that actually do the chemical work of turning hydrogen sulfide into sulfate and turning CO2 into sugars. They live inside specialized cells of this worm, and they are able to control the growth of the host cell so that it doesn't eat them up. And so there's a lot of interest from cancer research in how we can control cell growth using different chemicals that are produced by like these bacteria, for example. So that's one area of interest from biotech. Okay, so back to the evaluation framework. What's there? Specialized at hydrothermal vents, where we have these polymetallic sulphides. We've got specialized animals and microbes. 80% of them are found nowhere else on the planet. And there's also regional endemism, which means that there are some regions of the ocean that have some hydrothermal vent species that aren't found in other places. The scientific value, I hope I've managed to convince you that it's very high. Culture value as well, because people love to see videos of black smoker vents and beautiful high biomass organisms, and potential economic value of the organism, not the ore, is high primarily because of the interest from biotech. Recovery trajectory, well, we know they have a high capacity for rapid colonization, but they do need to have mother populations nearby. So spatial planning wise, here's one example of, I remember Nautilus Minerals that produced those machines I was showing you earlier. This was their plan for exploiting one site here called the Salwara 1 site near Papua New Guinea. So what they were going to do, this is a big mound of sulfide. It's about 150 meters across here. So they were going to come in and start mining in the middle. So the currents are coming from this direction, bringing larvae in from another reserve site out here somewhere. So they said, okay, what we'll do is we'll start mining in the middle here, and we'll work our way to the outside, phase 1. So that means that as we move away from here, larvae can come in and colonize in behind the machine. And then we'll swing around here and we'll start phase 2 and we'll work our way back to the middle. Whether or not that was a good idea or not remains to be determined. No one's ever done this, but that's one idea of sort of small scale spatial planning. And as you can see here in this map, these are what's called biogeographic provinces. So these are areas where we have unique species at these deep sea hydrothermal vents that are found nowhere else. So there's one here, there's another one near Japan, one off the coast of North America, one here, one there, and then one in the Atlantic. And they all have similarities in terms of the types of organisms, but the species are different. So you can't just say, well, let's just wipe this area out and we're not going to lose anything. We'll leave this one alone because we'll be losing the species that are unique to this area. Okay, manganese nodules. The last one in terms of mining operations and its impact. So these are the nodules. I said they form, as I mentioned to Joe, in areas where there's really low flux of a particular material down to the seafloor, really weak bottom currents at depths of 4,000 to 6,500 meters. These things take millions of years to form, but they stay sitting on the seafloor because of the fact that there's no sediment coming down to cover them up. And they're forming directly by precipitation of metals from seawater. So the fauna that we find on manganese nodules, well, they're the mobile fauna, swim around, and most of them are predators or grazers. Then there's some organisms that are attached directly to the nodules themselves, like this little mini sponge here. And then there are organisms that actually live within the sediments, like this brownish manganese-rich sediment we see here, has all sorts of things like nematodes and polychaete worms and foraminifera that are in many cases unique to this part of the world. And the scary thing about manganese nodule mining is the scale of these operations. So this is the area I showed you earlier of what's called the Clarion-Clipperton fracture zone, which is essentially where the biggest manganese nodule province in the ocean is about the size of the continental US. And this shows you some of the lease areas within the zone. So these operations will need to be anywhere between 10 and 100,000 square kilometers in size in order to be economically viable. So that is huge. We wouldn't get away with open pit mining on that scale on land, but no one sees it. So evaluation framework for nodules, really high diversity, and we're still counting. Are they rare and unique? Possibly, especially the fauna that lives on the nodules. Scientific value, this really is a huge reservoir of species, and this, because they occupy such a huge area, it really is key to understanding the ecology of the abyss and the capacity of the ocean to absorb and hold CO2. Culturally, well, they're kind of boring, right? They're just little lumps of whatever on the seafloor, and it's really hard to get people excited about them. There's no black smoker vents or spectacular this and spectacular that. It's just a muddy bottom with nodules on it. So there's work that needs to be done there. Economic value of organisms living there, and that's still kind of an unknown. And the recovery trajectory is really slow. So this is an experimental disturbance that was done in an area of manganese nodules. We see them sitting here, where some scientists came down and essentially dragged a dredge along the seabed for about 1.5 kilometers. And we came back 26 years later, and guess what? The hole is still there. So this essentially tells you, otherwise, if you did this in shallower water, bottom currents, tidal currents would eventually just sort of erase this scar, and we wouldn't see it anymore. So it's going to take a very long time. And so, take this and multiply it by 10 to 100,000 square kilometers, so you can appreciate what we're dealing with in terms of a recovery trajectory. Spatial planning wise, as I mentioned, these are really large scale operations. There are some buffer zones that will need to be established to protect similar large areas. And in the Pacific, in this province here, we have to think about both east-west and north-south gradients in terms of the species that are found there and the types of productivity. And the sediment plumes that are generated by these mining operations, they can travel up to 100 kilometers away from the mining operation. So if you're going to create a buffer zone, you don't want to have it next door. So imagine that this is, the center of a mining operation here, and it's 100 kilometers. Oops, sorry about that. 100 kilometers on either side. We're going to have to create buffer zones that are a long way away from any mining operation, and these will need to be buffer zones that also have nodules on the seabed and the nodule fauna. Okay, so I'm going to stop there because for questions, I'm going to go into something new now and talk about monitoring technologies and how we can monitor the environmental effects of these mining operations. Any questions?
Well, I'll ask one more.
Okay, go ahead. It's your prerogative.
Okay, seaweed. You spoke of it very early. I've read recently that seaweed can be processed, mixed with cow food, and then that lowers methane. But so the question
Yes.
is, uh, if we harvest the seaweed, besides the disruption generally of harvesting it, there must be some animals down there that eat seaweed, and they're not going to get seaweed anymore. Is it a
Good point. So what's being looked at now is kelp farming as a way of increasing productivity of kelp for both for food for livestock, and also there's a number of groups now they're looking at kelp farming as a way of sequestering CO2. So you essentially have a kelp farm, you produce a whole bunch of kelp, you bundle it up, and you take it out to sea and sink it, and all that carbon goes to the bottom. Well, don't get me started on that one, okay? But out here in the deep sea, some of the kelp that's produced and the seaweed that's produced naturally in coastal areas does work its way out to the deep sea. In fact, I'll show you an example of that when I'm talking about the technologies here. So, but most of the food for the animals in the deep ocean comes from plankton production in the surface ocean. Whereas if you're closer to the continents, kind of at the bottom of the continental slope, yes, you'll get a little bit of seaweed that'll sink and kind of wash its way down the slope. But if you're out here in the blue abyss, you're entirely dependent on plankton production in the surface ocean.
Any other questions?
Any other?
Yeah.
Okay, so I'm just going to give you some examples of how we can monitor the impact of these mining operations in a place that's really hard to get to, right? You can't just jump in your pickup and go out there and monitor things. You need technology to mine it, and you need technology to monitor the impact of mining. So a lot of environmental monitoring in the offshore ocean is essentially, ship-based monitoring, like using the same tools we use for research. So we can sample sediments with things like this box core here that you lower down on a wire rope from a ship, goes down to the seabed, and takes a bite out of the seafloor, about a quarter square meter of seafloor. You bring it up, and you can look at the animals that are in it, and measure biodiversity and know whether or not it's normal or low diversity, and eventually build up maps of where species are and how abundant they are in different parts of the ocean. This is a coring device here. These are actually tubes that are inserted in the sediment, do something similar. Or we sample the water column, do chemical measurements, looking at, in this case, we're measuring dissolved oxygen in the water column. Or we can, the ships can deploy vehicles that'll go down and map and scan the seabed. So a lot of it uses oceanographic research vessels like we see here, and it is essentially what we call ship-based monitoring. And then if you really want to get down there to the seafloor and see the damage, you need to use something like scientific submersibles. The only submarines that we have that are capable of going to great depths. Most military submarines, they'll stop at 500 meters, and there's not really. You just have to have you have to have a spherical hull before you can go any deeper than that. So this is a human-occupied submersible. This is the Alvin. It's been operated by the Woods Hole Oceanographic Institute since the 1970s. And it's deployed from a mothership or support vessel that essentially puts it over the side. This is what it looks like. There's a sphere here, personnel sphere, and a couple of mechanical arms out front. And every day, 3 people go down on the sub. So you've got a pilot and 2 scientific passengers. And you go down for the day. They usually spend about 5 hours on the bottom, collecting samples and making measurements. And then you have to come up by the end of the day because you're not allowed to stay down in the dark in case there's an emergency and you have to surface in the dark. They can't find you. So you spend the day down there. I've done about the early part of my career, maybe 50 or 60 dives in submersibles like this. But this is kind of old technology now. And what we use now are remotely operated vehicles, ROVs, that are a bit like the mining machines, okay? Everyone sits in a control room on the ship. A crane deploys the vehicle over the side, and then it operates on the seafloor, tethered to the ship by a fiber optic cable that also provides power. And this is the pilot sitting up here, and this is a bunch of scientists sitting in behind, following a dive. The advantage there is a lot more people can participate in the dive. There are no safety issues for people that are involved in the dive. And you can spend days on the seafloor mapping, sampling, et cetera. You don't have to come up for air or to go to the bathroom because, by the way, there's no bathroom in Elvin. When you got to go there, and you bleach bottle. And if you need to want to have lunch or you go have a nap, you can just leave. Someone else will replace you. And I just think it's a way more efficient way to work. It's not the same buzz as going down to the seafloor in a submarine. I'll grant you that, but you certainly get a lot more work done. And then there are what are called underwater observatory technologies, where we can have essentially sensor platforms on the seafloor that are either self-powered or connected by cable to shore that allow you to monitor a lot of things on the seabed. The group that I work with, the Ocean Networks Canada, we have a number of cabled observatories in the deep sea. This one here is at a hydrothermal vent. There's a probe here in a black smoker vent that's been monitoring this black smoker vent for 10 years now and sending data back to shore. Takes a measurement every second. And then we can even have remotely operated vehicles connected to these. So I'm going to tell you a little bit about this submarine canyon here off the coast of Vancouver Island, where we have some cabled observatory technologies deployed that could be used for monitoring some mining operations, just some examples of the tech. And I'm going to introduce you to Wally. So Wally is a mobile cabled observatory sensor platform. So essentially, Wally is a tracked vehicle about the size of a quad that people use to destroy the wilderness. And Wally has a whole bunch of sensors up front here. These tell you essentially where all the sensors are. Wally is tethered. There's a tether here. It goes back to a sensor platform, which is then connected by a cable. So here's where Wally lives, down here in the bottom of Barkley Canyon. He's connected to a sensor platform, which is connected to this fiber optic cable, which is connected to this node here, and then it goes all the way back to shore. So Wally is operated over the internet by operators based in Germany, and essentially goes out and does surveys. Wally, because it is such good German technology, can spend several years on the seabed without servicing, except that once in a while we need to go down there and do a little bit of cleaning up. So here we are with the ROV approaching Wally on the seabed, and we're going to essentially clean Wally's camera dome. And the operator is in Germany is turning the vehicle around so we can meet face to face. There's a horrible hagfish there. And this is a toilet brush we borrowed from the ship. And we're now just giving the camera dome a little scrub here, getting off all the biofilm, so Wally be good for. And now we're just doing a little bit of final detailing. We're using a suction hose on the ship and final polish, and good. Now Wally's good for another year of working on the seabed. Okay, that's just some examples of the type of tech. Now, I did talk a little bit about biotech interests, particularly in deep sea. So I think we should talk a little bit be a little bit realistic about this. So there's the promise of the genetic resources of the deep sea. Okay, this is, for example, a quote from the Norwegian National Strategy on Marine Bioprospecting, a source of new and viable wealth creation. As I mentioned, there are hundreds of thousands, if not millions, of animal species in the deep sea, and the diversity of microbes has yet to be quantified. And there are some real examples of antitumoral drugs that are derived from marine organisms. This one is called Yondelis, or tribecadin. It was developed by a Spanish company called Farmamar from this squishy-looking organism here, which is a colonial tunicate. And this drug here is now approved for treatment of ovarian cancer in 57 different countries. So that's the kind of thing that gets venture capitalists excited. Now I'm going to throw a wet blanket on it. Okay, so the reality is, in terms of developing drugs from marine natural products, if we go from collection of a sample in the ocean, screening of the sample, getting bioactivity hits and then leads, and then taking it all the way through clinical trials and marketing a commercial drug, we're talking about a process that can take 15 to 20 years, costs almost $1 billion per drug. And as you can see, we go from a lot of samples down to one drug, to the point where there are currently, since the beginning of this kind of research over 100 years ago, 17 drugs from marine organisms that are approved for clinical use by the US FDA. So here's the the table here of these approved marine drugs. And if you're interested in learning more, you can go to this website here, and it's updated every few months. But since they first started tracking this in 1969, we're now up to about 17 approved drugs, and there are similar numbers that are in different phases of clinical trials. And clinical trials don't always result in commercialization of the drug, because some clinical trials fail. So lots of promise, but not too many drugs yet. And what's interesting is we look at, most novel marine compounds that we see on this map here are coming from coastal waters, because the access there is the easiest. This is the famous coral triangle here in the Southwest Pacific. And, even along the coast of North America and South America, we can see there's a lot, and very little from out of the deep sea. And this is primarily an access issue. There are, thousands of scientists collecting samples and doing research in shallow coastal waters, and only a few hundred working in the deep sea. Another fast-growing sector are the marine nutraceuticals. So these are essentially things like, algal extracts and collagen creams for aches and pains. These are things that don't need clinical trials. And a lot of them are being produced from fish waste or harvested algae, as we were talking about earlier. So there's a lot more money in this right now. And 2017, there was about $180 billion in sales globally. So way more than we're getting from those 17 FDA-approved drugs. But interestingly, there is a growing commercial interest in marine genetic resources. So, for example, look at the statistics here. This is, the number of species that have patented sequences, gene sequences that have been identified and patented. And these are the number of sequences that have been patented. So this is the total number. So there's about, let's say, 850 species for which we have patented sequences, and then somewhere in the order of 12 or 13,000 actual sequences. So a lot of these species have multiple sequences that are being patented. So it costs money to work patents through. So there's an interest in this realization of potential. But then there's also an interesting article which was published recently. Is Big Pharma going to get it all here? Will this access and to marine genetic resources essentially be limited to developed countries, and the rest of the world is just end up paying, buying drugs from them? We all went through this, if you remember, when the first vaccines were developed for COVID-19. There was a bit of a debate about the fact that people in developed countries had way more access to it than those in developing countries. All this, the same game is playing out here. All right, so the battle for the abyss, which was the title of my talk, who are the players here? Well, and what's the game? You can see there are all sorts of different logos here in deep, vent base, and Dossier. These are all groups of scientists who are interested in the deep sea, or workshops being held different places. And here are some, here's a map showing some of the German and French license areas that are licensed by the International Seabed Authority. So we're talking about use conflicts. So mining interests, well, we've gone through that, right? They're going to exploit the crust, the nodules, the sulphide, and cause a lot of physical damage. Deep sea biologists, there's approximately 600 of us worldwide. It's an expensive area of research. So you need access to big ships and ocean-going submarines and all that tech that I was showing you in order to do deep sea biology. So we're a privileged few. And whereas, like myself, I started doing deep sea research early in my career because I wanted to get away from pollution. I found it too depressing. And now I found myself, a couple of decades later, feeling like I have to speak up here because this environment that I've spent 20, 30 years studying now is being threatened at a scale that is just mind-boggling. And we're now at a point where a lot of conservation NGOs who were just like those ladies sitting around the tea table there, didn't really know much, didn't really care much about the deep sea. They are turning their interest to deep sea conservation, and they are a growing lobby, particularly the IUCN and others. And meanwhile, we have big pharma here, they're very interested in the genetic resource potential, but they're kind of watching from the sidelines. But what's interesting is some of the major brands are trying to take advantage of this. For example, we've got Google, BMW, Volvo, and Samsung are saying, we are not going to build our products with metals that come from the deep sea. So they're taking a stand. Obviously, it's all about corporate image, and they know that they can afford to take this stand. They can source their metals somewhere else. But it's at the point now where major corporations are feeling like they need to be on one side of the debate or the other, or just duck and hide. But certainly when big corporations like this start speaking out, it does raise the profile of the whole debate. And researchers like myself who were only interested in the ecology of these are now starting to publish papers that are, this one here, for example, it's a primer for doing environmental impact assessment of mining. And then myself and some colleagues, we published this paper on in this book on environmental issues of deep sea mining. Talk about taking sort of an ecosystem approach to impact assessment, a bit like I was showing you earlier. So regular run-of-the-mill academic scientists are now suddenly becoming interested in this. And here we have where the debate happens. So the International Seabed Authority is a UN organization that was established in 1994 under the UN Convention for the Law of the Sea. So they're responsible for regulating mineral exploration and mining in what is called the area. I'll show you what that is in a minute. And they are headquartered in Kingston, Jamaica. So like any other UN thing, this is the General Assembly of the ISA meeting once a year. A lot of people in suits sitting around with little headsets on because you've got translation booths up here. Sorry. So the area that they're responsible for, the International Seabed Area, that's all the dark blue here. So this is what this office in Jamaica is responsible for regulating. 50% of the surface of our planet. The lighter blues are within exclusive economic zones of various coastal nations, but the dark blue is where most of these minerals are, and this is what the ISA was set up to regulate. So how do they work? Well, right now they have underway what are called exploration contracts with member states. There are 161 member states in the International Seabed Authority, countries that have signed on to UNCLOS. And these are, here's an example of exploration contracts in the Clarion-Clipperton fracture zone where the manganese nodules are in the Pacific. And in order to have an exploration contract, a commercial firm has to align itself with one of the member states of the authority. So we can have, the government of the Republic of Korea here. This is there's their green area here. And everyone has their little piece. And so revenues for the International Seabed Authority come from these 15-year exploration contracts. So countries then have to, if you have one of these contracts, you have to go in and essentially survey the area, gather information on environmental impact, gather information on the economic value of the minerals, and do regular reporting to the ISA. And here's some more in the Mid-Atlantic Ridge, some of these polymetallic sulphide, belonging exploration contracts with France and Russia in the Pacific. These are Crusts in this part of the Pacific here, the contracts given to China and Japan. And then the Indian Ocean, there's a number of both manganese nodule and polymetallic sulphides. So right now, the ISA has developed an environmental management plan, because they are essentially responsible for not only regulating mining and avoiding it become kind of a Wild West, they are also responsible for managing environmental impacts. But if you read through this plan, you will find out that, okay, the International Seabed Authority, they have no way of doing any monitoring. They're leaving the monitoring up to the mining companies. You know how that works. And so we were kind of, working. I first got involved with the International Seabed Authority in the summer of 2000 when they invited me down to Jamaica to give a presentation on the biology of hydrothermal vents as they were starting to develop regulations for exploration, not exploitation, but exploration. And they were taking their time about this. And then Nauru, a small island state in the Pacific, got hooked up with a company called Deep Green, and they found this obscure provision in the UN Convention for the Law of the Sea that there's a trigger mechanism. A country can announce their intent to mining, and within 2 years, the International Seabed Authority has to come up with regulations. So they did this in July last year. So we've got 1 more year before the International Seabed Authority has to essentially produce regulation for mining and allow mining operations to begin. And a group of scientists got together and published this particular statement here. And what's interesting is that, as I mentioned, between the year 2000 and I think the last time was 2012, the ISA would bring me to their informational seminars in different parts of the world. I always found it very nice to be able to share my knowledge of the deep sea with different places. And the last time I was with them, I was having a conversation with a staff member who won't be named, who shared with me this detail that, we can hardly wait for mining to start because it's going to generate more revenue, which means we can hire more staff and have a bigger building. My jaw dropped to the floor at that point. This is the organization that's meant to be regulating mining, and yet they can hardly wait for it to start because all they can think about is growth. Okay, that brings me to the end of my talk, and I'm going to pronounce myself. Are we ready for deep sea mining? What do you think the answer is going to be? Not even close. Okay, I'm happy to take questions. I'm going to stop sharing here so you can see my face again. And over to you folks for questions.
Hillary, yeah, go ahead and read the chats.
Well, Diane had a question.
Yeah.
I was surprised that you were not enthusiastic about using seaweed to sequester carbon dioxide. I had thought that was quite a viable thing.
Good question. Okay, I'm concerned about it for 2 reasons. One, if we start commercially producing seaweed on farms at massive scales, the seaweeds are essentially pulling nitrogen and phosphorus nutrients out of the seawater that are normally being consumed by plankton that are at the base of food chains that are supporting fish that we are harvesting commercially. So there's concern there about the local impact. The second impact is, does this take us back to using the deep sea as a dumping ground? And what's going to happen if we start doing this at a massive scale? You drop tons of seaweed bricks into the deep sea on top of organism in an environment that receives very little organic matter input. How's this going to impact it? Obviously, locally, it's going to be the equivalent of what we've been doing in the past when we were dumping sewage sludge in the deep sea. It's going to smother things. Okay, we're going to have a few little patches. Is that worth it? I don't know, but I think we need to sit down and do the math on that one.
Thank you.
So 2 reasons: local impact and then impact on our friends in the deep sea.
Great, thank you. And Amy had a question.
I think you answered it, actually. I wrote here, how do we monitor what has been established? What has the world established about which country, I should say, which company can work in which part of the deep waters? And you really answered that with that great map of explaining the different areas and in the deep sea and the different countries that are basically, they can't say own, but they monitor that particular piece of sea.
Well, they are surveying and with the intent of eventually mining. So after the 15-year exploration license is terminated, they're allowed to renew it once. And then after that, they either give it up or you have to make an application for a mining permit.
Thank you.
Okay, Laura had a question and followed by Sarah.
Yeah, I think Sarah and I are sort of asking the same thing. What can we do to help this? This is destruction in the making.
Yep. I think you can support groups like the Deep Ocean DOSI, which is a Deep Ocean Strategic Initiative, and just talk about it, share this knowledge with people. I mean, we're still at the point, you know, that slide I showed at the beginning where most people don't know anything about deep sea, so they don't care. And we need to raise the profile here. And I think the best thing you can do, most effective thing you can do is tell your friends about it. You know, tell your neighbor over the back fence. Just start talking it up.
Okay, thank you.
I'd like to add a couple things to that too, because first of all, the little animals you showed, all of that was just so wonderful. I mean, I didn't have a clue about any of it. And so I feel like, you know, you've opened up a world of deep sea life for us. But in addition to that, my father, to make you feel like slightly better, my father was in air pollution control in the late 50s and in the 60s and 70s. And it was a thankless job because nobody wanted to spend the money on prevention.
Yeah.
And so to hear that you know, thought, well, let's go underneath. My question actually concerns when you were in New Zealand for a time. Did things look any different from down under in the way of, or is it now so obviously global that we just all got to get off our butts and do something?
It's the latter. I mean, globally, most developed countries anyway are very much aware of this. New Zealand, for example, has some volcanic ridges within its territorial waters, as well as an area of phosphate mining there's been an application for mining that was refused by the government, and then they're coming back again. So they're very much clued into the deep sea mining, and a lot of the government scientific agencies are doing sort of impact type survey work, in particularly in New Zealand.
Thank you.
Yes, Susan?
We have our own history of mining in California, where gravel miners started taking gravel out of the Russian River and almost destroyed it before Dr. Martin Griffin got them to stop. And almost wrecked the water, which now serves 600,000 human beings in Sonoma County. So this is a small example of exactly what you're talking about.
Yes, and the scale of deep sea mining operations is even scarier. And you know, someone, you know, prior to my talk, I know someone sent Joe a question about, well, who are the locals who are going to care about this? And we are all locals. You know, when you're talking about something that's affecting 60% of the surface of our planet, that concerns us all. I mean, the deep sea is a huge and a very important part of our planetary life support system, and you can see how we've been using it. It's used, you know, it's absorbed a huge amount of heat from the atmosphere and kept global warming from getting, well, keeping it where it is today rather than getting way worse. So in many ways, we're all in this together, and it's the deep sea. It should be everyone's backyard, as far as I'm concerned.
Thanks. Roger had a question.
What are your requirements for deep sea mining, and what would need to happen for deep sea mining to meet your requirements?
Oh, good question. My requirements. I mean, as you can see, the type of mining is all very case specific, and you know, we just don't know enough. So, you know, and it's not going to be sustainably extracted because, you know, every one of these mineral deposits that we'll be exploiting there has taken centuries, if not millennia, to form. So question, I guess, is, you know, how much of it are we willing to give up in order to get access to minerals? Because as far as I can see, you know, any mining operation is going to be 100% destructive as far as any ecosystems that are associated with it is concerned. So it really comes down to, okay, how much, you know, what fraction of the manganese nodule ecosystem are we willing to take out. And we're not there yet in terms of understanding how important this area is for the ecology of the deep sea. Can we afford to lose 5%, 40%? We don't know yet. So I guess my criteria are really come down to, what is, we need to be able to quantify the impact and not at a global scale, really. Certainly I have a graduate student, a PhD student now working on trying to evaluate the potential economic value of the microbes that are associated with polymetallic sulphide deposits. And her goal is to demonstrate the value to society, potential value to society and biotechnology of the microbes that are about to be trashed by a mining operation. And it may turn out that, the value of the minerals is, what we're hoping to demonstrate, the value of the minerals is small compared to the long-term potential gains that we would have by exploiting the genes and chemical compounds that are produced by the microbes that live there. And that we can do sustainably. We don't need to go down and scoop up tons of material to exploit the genes of microbes. We just need a few. And we do it all in the lab. Once we've identified genes and enzymes of interest, we can just reproduce them synthetically in the lab, but we have to have models and examples to work from. And we learn more about these things every year, and the tools that we have for drug discovery are improving every year. So whereas a mining operation at a sulphide deposit might last 5 years, we could probably continue sampling and researching that same spot for a century, and continuing to develop new drugs as our technology and capability improves.
Elaine asks, is anyone monitoring illegal mining? What's the monitoring authority? Okay,
in terms of deep sea mining, there really is no illegal mining going on, because you couldn't get away with it. That said, there are places where there is illegal mining going on. For example, in Thailand, there's a lot of dredging for tin nuggets near shore. Tin essentially gets swept down the rivers, and we have these sort of are called plastic deposits of tin. But in Thailand, they have a very pragmatic approach to it. There are zones, there's legal licensed mining operations, and then they have zones for illegal mining. I hope we don't have to go that way in the deep sea, but right now, that's the way it goes. Every country that's signed on to it, you just couldn't get away with it. It's because of the scale and the technology that you would need to produce it. No mining company would take that risk.
Susan wonders if you could share the slideshow. She would like to show it to other people.
Certainly, yeah. I could forward that to Joe.
Thank you.
I could put it in Dropbox, for example, and send Joe a link. Yeah, I'm happy to share.
Well, Sarah has a follow-up comment.
Yes, the follow-up is just, the irony of us and these wonderful photos coming to us from outer space as we are enamored of that. And you talked about the word romantic in your intro, the romance of all of that, forgetting about our beautiful little planet and some of its treasures just because we can't see them. And it seems to be a motivator.
It's a motivator. There's a group called the Marine Minerals Society that has an annual conference. They've been meeting since the 1970s. And when I first started knowing something about deep sea mining, I went to a few of their conferences, and it was amazing. These people are believers. Most of them are geologists, and they, most of them were kind of at the end of their career, and they started off in the 1950s and 60s on their careers, and they were just fascinated by the idea of mining the deep ocean. Like we talk about asteroid mining today as with a kind of a romantic, wistful glint in our eye, thinking we'll go out into space and we'll harvest minerals and we'll keep our planet going. Well, that was the attitude to deep sea mining, and they still meet and talk about it. And I stopped going to their meetings because it got, well, all they talk about is dredges and pumps and and mineral grades. And I've gone and given a few sort of environmental talks, and someone will take me aside after and say, "Why did you come to this meeting? What's in it for you?" So they carry on in their little world, and well, it's the way it is. There's a world called economic geology. These are geologists who know a lot about minerals and their value to society, and I have a colleague works in that field, developing methods for essentially evaluating the economic value of one of these deep sea ore deposits. So, because that's not easy to do. And when you do it on land, you find an outcrop somewhere, and then you say, okay, how big is this thing? Well, let's drill and take some cores. Well, doing that in deep sea is a way different story. So you need to use sonars and remotely operated vehicles, and coring in the deep sea is really challenging.
Any other questions? It's 4:30 just about, and you've been more than generous with your time, Kim. And we really do appreciate it at Ashby Village and all of our entourage. And so once again, thank you very much. Bravo.
Thank you for joining me. It's been fun. I love the questions, and especially the hard ones.
Okay, well, again,
Like,
yes.
Yeah, and it always makes you think, I can ask a little technical question, then I can't remember who asked me the question. Okay, what's your criteria for making this happen? And I'm thinking, okay, I'm on the spot now. What am I going? And so I like questions like that because they really make you think, as opposed to just recite something that you've already said. So keep doing that.
Okay, well, enjoy your time in Vancouver.
I will very much. Thank you.
Okay,
It's a sunny day here for once. Okay,
Thank you.
bye all.
Bye-bye.
And I will forward my slides to Joe. Might not get to it today, but within the next week or so.
That's okay.
Thank you.
Thank
Thank you
you.
very much.
Okay,
Yeah.
Bye-bye.
bye-bye.
Thank you. Bye-bye.